In this video, we will talk about the basics of analytical geometry, and we'll start with vectors in two dimensions. Let's start with the definition here. A vector V, which is typically denoted by V arrow, sometimes it's denoted by a bold V, and sometimes it's denoted by V underline. So they all are, representation of a vector. Now, a vector is a directed line from an initial point to a final point. Now remember that we are talking about two dimensions here, so therefore the initial point will have a coordinate of x and y, and a final point also will have a coordinate of x and y. Okay, so it's just a directed line between an initial point and to a final point. So our initial point can be pi and final point can be pf, and this is my line and typically denoted by an arrow from the initial to final point. And if the initial point is 0 0 or the origin, then it is called the position vector. Okay, now we talk about the vector space. Okay, so vector space is v2, or you can this is not the only notation to use vector space. So a 2D vector space is a set of all vectors such that the following two conditions hold. So if we add two vectors, we can add them by adding their corresponding x and y coordinates separately. Okay, so we can say u1 u2 plus v1 v2, this is equal to u1 plus v1 and u2 plus v2. And if we multiply a vector by the scalar, we can multiply that scalar by both the x and y coordinates. If that is true, set of all the vectors that follow these conditions or fulfill these conditions, they form a vector space in two dimension. Okay, and then again, another simple definition is that a magnitude of the vector is given by just their x component squared plus y component squared and square root. Okay, now if you multiply a vector by a scalar, then its direction does not change unless that scalar is 0. Okay, so direction is the same if k is positive, the direction is the exact opposite, so the only thing which changes is the arrow. Okay, so direction is exactly the opposite if we have k negative, and is the same with k positive, and it is 0 if k is 0, then we get a 0 vector. Okay, then any vector v1 v2 can be represented by v1 times 1 0 plus v2 times 0 1. So then this is convenient that we can now define two unit vectors. Now note that the magnitude of this guy is 1, the magnitude of this guy is also 1. We can define two unit vectors, one as I, which is 1 0, and one as j, which is 0 1. So this is a very standard practice. So any vector, this can also be written in this form. And a unit vector of the unit vector in the direction of v is v divided by the magnitude of. So if we just divide any vector by a magnitude of v or multiply the scalar 1 over v to the vector, then we get the unit vector in that direction. Okay, now we are interested in a question that when can a vector be formed from a linear combination of two other vectors. Okay, when can a vector, it means any arbitrary vector we choose, and we can choose any arbitrary vectors to be checking whether their linear combination exists for those two vectors or not. Okay, so let's say we are interested in saying that our z is some vector. This is equal to some constant p times a vector u plus some constant q times a vector v. Okay, so what did we say? So then if z1, if z is z1 and z2, this equates to p times u1 and u2 plus q times v1 and v2. Okay, so then this equates to z1 is equal to p times u1 plus q times v1, and z2, this is equal to p times u2 plus q times v2. Okay, so now we have to find the constants p and q for the values of u1, v1, u2, v2, and given z1 and z2. Okay, now let's say that u and vector v have same or exactly opposite direction. This means that I can say u, this is equal to k times v, where k is a scalar. Okay, so this means that I can say u1, this is equal to k times v1, and u2, this is equal to k times v2. Let us plug it here. So I can get z1, this is equal to p times k times v1 plus q times v1, which means I can take v1 out and I get pk plus q. Similarly, z2, this is equal to p times k times v2 plus q times v2. Then I can take v2 out and I can say pk plus q. Okay, so this means that z1 is some constant times v1 and z2 is some constant times v2. So I can say the vector z is pk plus q times v. So this means that if u and v have the same direction, then z has to be the same z has to be directed in the same direction. So this means what? This means z cannot be arbitrary. Okay. Okay. So now, other than that, if this condition is, if u and v are not, I mean, non-zero vectors, obviously, so we can say u and v are non-zero vectors. So this is another condition. It's obvious, but it's good to write them. Okay. So the point is that if u and v have the same direction, or they are parallel or non-parallel, then, or anti-parallel, then z cannot be arbitrary. Z has to have restricted in the same direction. Now let's see an example. We will see two examples here. We say, okay, our z is, let's say, -1 and 2. This is my z. And let's say 1 and 3 is my u. And let's say 2 and 5 is my v. Now we can see that this cannot be written as a scalar multiple of this, right? Because we can clearly see that 2 is some different multiple of 1 and 5 is some different multiple of 3. So then u and v are not parallel. So now you will see that this is possible. So now we'll say -1, this is equal to p times 1 plus q times 2, which is equal to p plus 2q. And then the other equation is 2 is equal to p times 3 plus q times 5, which is equal to 3p plus 5q. Okay, so now so then for this case, our p, this is equal to 9, and q, this is equal to -1. So then we can say that z is 9 times u minus 1 times, it should not -5, -5 times v. Okay, so then this is possible. Now let's see, we say our z is the same, but now let's choose up two parallel vectors. Okay, and then we say let's say 1 3 is our u and in order to select a parallel vector, we can multiply any scalar by this. So let's multiply it by -2. So let's say -2 and -6. This is my v. Okay, now let's see the equations. Our equations becomes -1 is equal to p times 1 plus q times -2, which becomes p minus 2q, and this becomes 2 is equal to p times 3 plus q times -6, which becomes 3p minus 6q. Okay, so I can write this is equal to -1 and this is equal to 2. If I multiply this whole equation by 3, I will get 3p minus 6q. This is equal to -3, and I can get 3p minus 6q, which is equal to 2. So the same thing, 3p minus 6q here and here, but they are equaling two different things, so this is not possible. Okay, so if in the case where u and v are parallel, we cannot have an arbitrary z, a linear combination of u and v. Okay, so this is what our conclusion is, that if the vectors, these two vectors are non-parallel, then this is possible. If they are parallel or exactly opposite, then it's not possible. Okay, so this is it for a brief introduction of vectors in two space, and how can we form a linear combination of two vectors to remain in the same vector space. So hope it was easy to understand. Thanks for watching. Hope you liked the video.